Okay, so this is chapter 15, number 2 and 3. So if you look at number 2 in here, we're given that the force between two charges, A and B, is equal to 2.62 newtons. And we're given that the distance that they're separated is 13.7 times 10 to the negative 3 meters. So that's 13.7 millimeters. So this is the force, and this is the distance they are apart. So if I think of my Coulomb force equation, F equals K Q1 Q2 over the radius squared, I can look at these two, like here I should put that this is QA and QB. I can isolate and solve for QA, QB. And the way I would do that is I would multiply both sides by radius, and that should be squared right there. So I multiply by the radius, put that on the top, and I divide by the k, so I divide both sides by k. And what I've done is I've isolated QA and QB. So now I'm just plugging in numbers. My F was 2.62. My radius is 13.7 times 10 to the negative 3. I square that, and I divide by the Coulomb constant. Alright, and so that gives me something. I just wrote a squiggly line here to represent whatever that answer is. So now I'm asked for what's the force when we move these two charges, like they're originally, like we're not given if the force is positive or negative, but I have these two charges, and they originally have this distance here. Well, if I move them to a farther distance, what is the force going to be? So we know the force is going to drop the farther away it gets. But I'm going to come over here and I'm going to set up my Coulomb formula again. But now this is a different radius here. So I found QA, QB from the first one. So then that would, whatever your value for this would go right here. I have my Coulomb constant, and I have my radius squared. So if I plug this in, and this is just substituting the values in, I would get an answer here. So I'll let you guys do the calculation. Okay, this next question is pretty difficult. So they talk about bulkheads in a spaceship, and I actually had to go and look up what's a bulkhead. But if you look that up, it's just two different compartments in a spaceship or an aircraft. So I think it's easier just to think of them as two metal walls. So we have two metal walls here, and we have this setup where we have two charges that are like charges, and they're repelling each other. So that's causing a tension in this cord. So I have two charges with two forces acting on each, like the repulsion force is causing them to repel, and I'm given a tension in this cord, and the tension in the cord is due to this repulsion. So in order to solve for my Q, I'm going to set up my Coulomb force, and I'm going to say K times Q, and then the second charge is 2Q over my radius squared, and I'm going to set that equal to 2.5 newtons because I'm given that the force of tension is 2.5 newtons. So this tension is 2.5. So I'm going to set these equal to each other. So this force has to equal this force because it's in equilibrium. Alright, so if I do that, I can come down here, and this is just rearranging the formula. So this radius squared, I want to put this on this side. So I'm going to multiply both sides by radius squared. So I did that here. Now I'm going to isolate my Q squared. So I'm going to divide both sides by 2K. So I did that here and divided both sides by 2K. And then since I'm trying to find Q, I take the root of both sides. And I just want to make go back and point this out. This is q squared because I have q times q here. So I have q times q, this is q squared. I have my 2, and then I have my k. So once I isolate q, I have to take the root of both sides. And again, I'll let you plug this into your calculator and figure out what that value of q actually is. Okay, so part B, this says if we know these charges, what's going to happen? What will happen if we let this system just be at rest for a while? Like ultimately, what's going to happen? And this goes back to charging through or inducing a charge in something. So you can think of like if this is a positive charge, well, a positive charge, it might be easier. Well, a positive charge. Well, if we look over here, if these are positive protons and electrons over here, as this positive charge gets closer and closer, it's going to cause the electrons to come over to this side of the wall. So it's going to negatively charge that wall. So this charge would be negatively charged, and with this positive charge, then they would be attracted to each other. So this thing's going to slowly go over in this direction. This is inducing a charge as well, but since this is 2q, it's gonna move in this direction. So we've induced a charge in the bulkhead or the wall. So slowly over time, this will drift to the right. And again, it's because this positive charge is causing all the free electrons to run over here, and that's leaving an excess of positive charges over here. So this acts as a negatively charged wall, and then negative and positive attract each other. Alright, I hope that helps. I can help in class too if you need further explanation.